The Cascades Volcanic Belt is activating, and all magma chambers are filling fast because what's happening along the entire West Coast volcanic chain suggests we could be witnessing the countdown to the most devastating eruption sequence in North American history. Picture a 700-mile chain of deadly volcanoes stretching from Northern California to British Columbia, all suddenly showing signs of life at the same time. Mount Shasta, Mount Rainier, Mount Baker, Mount Hood, every major peak is registering unusual seismic activity, ground swelling, and thermal signatures that indicate magma is rising from deep within the Earth. But here's what has volcanologists in complete panic. This is not normal volcanic restlessness. Satellite data shows that magma chambers beneath multiple Cascade volcanoes are inflating simultaneously, something that has never been recorded in modern history. The entire volcanic belt appears to be responding to the same deep geological trigger, like a massive underground pressure system that is pushing molten rock toward the surface. The most terrifying discovery came from comparing current activity with geological records from the last time multiple Cascade volcanoes erupted in sequence. That event, over 7,000 years ago, buried the Pacific Northwest under feet of ash and triggered climate changes that affected the entire planet. Are we watching the early stages of a Cascade super eruption sequence, or has something deep beneath the North American continent awakened that could turn the entire West Coast into a volcanic wasteland? From the southern sprawl of Redding, California, to the rainy suburbs of Seattle and the green valleys near Vancouver, millions of people live, work, and raise families in the shadow of Cascade volcanoes. These are not remote wilderness peaks. They stand guard over towns, highways, schools, and hospitals. Ording, Washington, a small town of just 7,000, sits squarely in the path of Mount Rainier's Lahar hazard zone. Puyallup and Sumner, with a combined population of over 60,000, lie downstream, their neighborhoods mapped out in bright red on official hazard maps. Farther south, the city of Portland's eastern edge brushes against Mount Hood's Lahar and ash risk, with over 150,000 people in Sandy and the surrounding Clackamas River Valley exposed to possible flows. In total, more than 4 million people live within the mapped hazard zones of the Cascade chain. Zones defined not just by the reach of lava or ash, but by the cold mathematics of topography and river channels. Interstate 5, the busiest highway on the West Coast, crosses Lahar paths from both Mount Rainier and Mount St. Helens. Hundreds of miles of state highways weave through valleys that could become choked with mud and debris in under an hour, including Oregon State Route 22, California State Route 89, and others. Hospitals like Multicare Tacoma General, Peace Health St. Joseph in Bellingham, and Shasta Regional in Northern California are all situated inside or on the edge of these risk zones. Their emergency rooms could be just minutes from neighborhoods that would need to evacuate if an eruption or mud flow began. The numbers reveal a corridor of vulnerability. In the Puget Sound lowlands, over 1 million people live in areas mapped for possible ashfall from Rainier or St. Helens. In Oregon, 20% of the Portland metro area sits within Mount Hood's ash and Lahar zones. In Northern California, Redding and nearby towns, totaling more than 80,000 residents, face the threat of Shasta's ash and debris flows. Even small towns such as Weed, Sedro-Woolley, and Estacada are not immune, each with thousands of residents and only a handful of escape routes. Critical infrastructure weaves through these danger zones. Power lines from the Bonneville network, water supply aquifers, and major bridges all intersect with paths that, on hazard maps, look like scars running from volcano to city. For many, the threat is invisible, masked by forests, rivers, and the familiar routines of daily life. But the hazard is mapped, measured, and real. The next section of the story will focus on what happens when minutes matter, and why the scale of human exposure across this volcanic corridor turns every uptick in activity into a race against time. The Cascades Volcanic Belt is activating, and all magma chambers are filling fast, because what's happening along the entire West Coast volcanic chain suggests we could be witnessing the countdown to the most devastating eruption sequence in North American history. When a research group from Cornell University released the results of a seismic imaging project in early 2025, the scientific community took notice. Using a network of upgraded USGS and university seismometers, the team mapped the deep crust beneath the Cascades by capturing echoes from distant, powerful earthquakes. Those waves travel through the earth and subtly change speed when they pass through hot, partially molten rock. Their findings, published in January 2025, revealed something both remarkable and unsettling. Beneath 6 of the region's most iconic volcanoes, Mount Rainier, Mount St. Helens, Mount Hood, Crater Lake, Newberry, and Lassen, large zones of slowed seismic waves indicated the presence of partially melted magma bodies. Some of those bodies were as shallow as 3 miles beneath the surface, others stretched as deep as 9 miles. The study's lead author, Dr. Guaning Peng, described these zones as persistent, sponge-like reservoirs with melt fractions ranging from 3% to 32%. That means, inside these vast underground chambers, solid crystals and hot liquid magma are mixed together in proportions that have likely remained stable for thousands of years. But what caught everyone's attention was the pattern. All 6 volcanoes showed these partial melt signatures at the same time, mapped by the same method, and confirmed by independent teams using different seismic data sets. For volcanologists, this was both a breakthrough and a puzzle. On one hand, it confirmed what many had suspected, that the Cascade volcanoes are not dormant, empty shells, but rather house long-lived magma systems always on standby. On the other hand, the simultaneous detection of partial melt beneath so many peaks raised a new question. Could a deep geologic process be supplying heat and melt to the entire arc at once? The Cornell team stopped short of declaring a crisis, emphasizing that their imaging captured a snapshot in time, not a movie of reservoirs actively inflating. Yet the data forced a re-examination of what it means for a volcano to be quiet. In interviews, Dr. Peng and geophysicist Jeffrey Abers stressed the importance of context. Abers explained that these magma bodies are not new arrivals. They are a baseline feature of the Cascade Arc, present for millennia. What matters is not that they exist, but whether their melt fraction is changing. Still, the study's impact rippled through emergency management circles and made headlines in scientific journals. If partial melt is a constant feature, then the real risk lies in detecting the subtle changes, small increases in melt, rising temperatures, or shifts in seismic wave patterns that might signal the start of something much bigger. As the story moved from population maps and hazard zones to the hidden world deep beneath the volcanoes, a new sense of urgency took hold. The next step was testing whether these partial melt zones are stable or if something is quietly changing in the darkness below. West of the snow-capped Three Sisters peaks in central Oregon, the landscape has been rising, slowly, almost imperceptibly, for more than 2 decades. Since the mid-1990s, satellites and ground-based GPS receivers have tracked the ground here lifting by as much as 15 to 20 centimeters, a change invisible to the naked eye, but unmistakable in the data. This is not the sudden swelling that often precedes an eruption. Instead, it is a patient, persistent inflation, one that geodesists, like Dr. Michael Poland, have spent years unraveling, meter by meter, pixel by pixel. The process starts with satellites orbiting hundreds of miles overhead. Using INSAR technology, they bounce radar signals off the Earth's surface, capturing minute changes in elevation between each pass. Combined with a network of GPS stations anchored in the high desert, these measurements reveal a broad, gentle dome of uplift west of South Sister, covering nearly 100 square miles. The numbers are precise. From 1995 to 2018, the ground rose by about 1 to 2 centimeters each year, accumulating a total uplift of 15 to 20 centimeters. Modeling suggests this translates to a volume increase of roughly 0.1 to 0.3 cubic kilometers, enough magma to fill a football stadium hundreds of times over, but still a tiny fraction compared to the total reservoir beneath the volcano. Dr. Poland explains that what is happening here is a textbook example of localized inflation. Magma is intruding quietly into the crust, about 7 to 11 kilometers below the surface, spreading out like a slow-motion balloon. There is no sign of eruption, no swarms of earthquakes, no dramatic gas emissions. The inflation has continued at a steady pace for more than 25 years, unaffected by the seasons or short-term weather. This kind of long-term, isolated uplift stands in stark contrast to the sudden chain reaction signals that would suggest a coordinated awakening across the Cascade arc. The Three Sisters uplift story proves that magma chambers can fill slowly and silently, with no immediate threat to the communities scattered across the high desert. It also demonstrates the power of modern geodesy, how satellites and ground sensors can detect changes that would otherwise go unnoticed for generations. For scientists, this is both a reassurance and a warning. Inflation can be real, measurable, and yet entirely local, offering a baseline against which any future, faster signals must be judged. The lesson from Three Sisters is clear. Watch the ground, trust the data, and remember that not every rise is a rush to eruption. On the flanks of Mount St. Helens, the ground rarely sits still. For decades, banks of seismometers have captured a constant background of tiny earthquakes, sometimes just a handful per day, other times dozens or more. In the spring of 2025, the pace quickened again. Clusters of small quakes began popping off beneath the volcano, most too faint to be felt, but relentless in their regularity. Some days brought as many as 20 tremors, each one a brief jolt deep under the crater at depths ranging from 2 to 6 miles. To the untrained eye, these numbers might sound alarming. But for volcanologist Dr. Janine Krall, who has spent years cataloging every blip and buzz from St. Helens, the pattern was familiar. A restless crater, not a volcano on the brink. Krall's daily work involves scrolling through pages of seismic data, each spike on the graph a possible clue. She knows the difference between the sharp, brittle pops of rock cracking under pressure and the longer rolling rumbles that hint at fluids moving through ancient fractures. The 2025 swarm fit the classic St. Helens profile: shallow, repetitive, and spread out over weeks. There was no sign of the deep, low-frequency earthquakes that would suggest magma was pushing upward. No sudden bursts of volcanic gas, no ground bulging or tilting, and no heat signatures on satellite scans. Instead, the activity pointed to a slow, episodic recharge, magma trickling into a reservoir miles below, adding just enough energy to keep the system simmering, but not enough to break through the surface. The word that best describes it is recharge. This kind of unrest sets St. Helens apart from its neighbors. While the Three Sisters uplift is a study in slow, silent inflation, St. Helens is all about fits and starts, short bursts of seismic chatter that come and go, sometimes months apart. The episodic nature of these swarms keeps scientists on alert, but it also highlights the diversity across the Cascade arc. What looks like a warning sign at one volcano might be routine at another. Krall keeps a close eye on the catalog, aware that every episode adds a new layer to the volcano's history. The data show that since the 1980 eruption, St. Helens has produced thousands of these small quakes, most never leading to anything more than a brief spike in scientific curiosity. For the public, the distinction can be confusing. News of a seismic swarm often sparks questions about eruptions, evacuations, and worst-case scenarios. But Krall and her colleagues rely on a deeper set of signals. They compare swarm patterns, gas readings, and ground deformation across the entire Cascade chain, searching for evidence of a shared trigger. So far, the results are clear. Mount St. Helens moves to its own rhythm. Its magma system recharges in pulses, sometimes noisy, sometimes quiet, but always under watch. The lesson, Kroll says, is that no two volcanoes speak the same language. The real challenge is learning to listen and to know when the chatter is just that, and when it is time to worry. Deep beneath the Cascade Arc, a network of partially molten rock stretches for hundreds of miles, hidden from view but central to every debate about volcanic risk. To explain how so many volcanoes could show similar signs at once, geodynamic modelers turn to the low-velocity zone, a band of hot, ductile mantle that runs beneath the subducting Juan de Fuca plate. Seismic imaging reveals this zone as a kind of slow-motion river, where rock moves more easily and heat accumulates, feeding the crust above. Numerical models suggest that changes in mantle flow, whether from shifts in plate motion, slab rollback, or even subtle changes in the subduction angle, could in theory alter the supply of melt to volcanoes all along the arc. The question is whether these deep processes can synchronize activity at the surface. Dr. R.M. Allen, a leading geodynamicist, describes the low-velocity zone as a shared plumbing system, one that allows pressure and melt to migrate over months or years rather than centuries. In Cascadia, the mantle flow patterns are complex. Some regions show trench-parallel fast directions. Others hint at toroidal flow around slab edges. These flows can focus melt beneath certain volcanoes, but slab fragmentation and variable plate coupling often break the chain, preventing a perfect domino effect. Still, models show that a strong enough deep trigger, like a pulse of fluids from the subducting slab, could send a wave of melt upward, potentially raising pressures in multiple reservoirs at once. The timescale for such a process, months to a few years, falls within the window that modern monitoring networks can detect, but the evidence for a single arc-wide trigger remains circumstantial. For now, the deep plumbing hypothesis offers a framework. The Cascades are connected below, but each volcano responds to the flow in its own way, shaped by local fractures, crustal thickness, and the ever-changing dance of the plates. A sharp jolt at Mount Rainier's summit can set off a chain reaction that leaves almost no time to react. In the Puyallup River Valley, the warning sirens are programmed for a single, chilling scenario, a lahar racing from the mountain's glacier-clad flanks, barreling toward Ording at speeds that can reach 40 miles per hour. U.S. Geological Survey models show that, in some cases, the first wall of mud and debris could arrive in as little as 35 to 45 minutes. That's the window, less than an hour for thousands to escape from schools, homes, and businesses perched in the lahar's path. Civil protection officials in Pierce County know these numbers by heart. Their drills revolve around a race against the clock, with evacuation routes mapped and practiced down to the minute. The stakes are not theoretical. Every year, students in Ording rehearse the uphill sprint to safety, following lines painted on the pavement that mark the fastest way out of danger. The science behind this vigilance is always evolving. In the summer of 2025, new lahar sensors, capable of detecting the vibrations of a moving flow, were installed along Rainier's river valleys. By 2026, the network will expand, feeding real-time data to emergency managers and triggering automated alerts. U.S. Geological Survey spokesperson Alex Iezzi reminds the public that right now, the official alert level for the entire Cascade chain remains green. There are no signs of magma movement, no deformation, no cause for panic. But the monitoring continues, relentless and precise, because when minutes matter, preparation is the only defense. Today, the Cascade volcanoes remain closely watched, not because an eruption is imminent, but because millions live in their shadow. Scientific vigilance, not panic, shapes our safety. Real-time monitoring means that even ordinary unrest becomes a test of our preparedness, not our fear. In the Pacific Northwest, the greatest threat is not a sudden eruption, it is complacency. Nature's silence is never a guarantee. Stay curious, stay informed. Your awareness is the first line of defense. At 11:15 p.m. in northern Japan, what sounded like a powerful but ordinary earthquake suddenly triggered a nationwide megaquake advisory, the first of its kind since 2022. More than 90,000 residents evacuated as the threat of an even larger tsunami-spawning rupture loomed over Aomori's dark coastlines. Seismic experts warn the pattern matches the days before Japan's greatest modern disaster. But this alert, issued under new, untested criteria, has left officials and families fearing a catastrophic repeat. So what is about to happen next? Sirens cut through the cold December air as the ground convulses under Aomori's coastal neighborhoods. The shaking is relentless. Windows rattle, dishes crash to the floor, and in the span of a single minute, the familiar world fractures. On the main road out of Hachinohe, cars jam every lane as families abandon their homes, headlights weaving through a haze of dust and panic. Cracks split the asphalt, swallowing bicycle tires and sending a delivery van teetering onto its side. Parents shout for missing children, their voices barely rising above the wail of emergency alerts echoing from every phone, radio, and loudspeaker. A magnitude 7.6 earthquake, centered deep beneath the Pacific at 54 kilometers, has just torn through the night. Within minutes, the Japan Meteorological Agency issues a tsunami advisory, warning that waves could reach up to 2 feet. In the darkness, people scramble for higher ground, some clutching emergency bags packed after years of drills, others barefoot and dazed, trailing behind neighbors who know the evacuation routes by heart. Tsunami waves arrive at the fishing port. The first wave, 60 centimeters and just under 2 feet, rolls in, swirling boats against the concrete piers. It is not a wall of water, but it is enough to sweep away anything left on the dock. Across Aomori and into Hokkaido, evacuation orders ripple outward. 90,000 residents are told to leave immediately. Shelters fill with old men in pajamas, mothers holding babies, teenagers frantically texting relatives. The city's power flickers, then fails. Without streetlights, the only illumination comes from the red glow of hazard flares and the blue-white beams of emergency workers' flashlights. On the outskirts, hospital staff form a human chain to move patients onto buses, their stretchers bouncing over broken pavement. In the chaos, every second feels stretched thin. Some families are separated as fathers double back for a missing pet or a forgotten medication. Others squeeze together in the stairwells of reinforced evacuation towers, listening as the building groans with each aftershock. For many, this is a nightmare they have rehearsed but hoped never to live, a drill turned real. The memory of 2011 is sharp. Grandparents whisper stories of the black water that came without warning, of friends who never returned. Tonight, every rumble underfoot feels like a countdown. By midnight, the official count is already climbing, dozens injured, roads impassable, and the threat of something even larger hanging over the region. Outside, the sea is eerily calm, but the fear is electric. No one knows if this is the main event or just the beginning. In every shelter, people grip their phones, waiting for the next alert, the next siren, the next order to run. The Japan Meteorological Agency's headquarters glowed with activity as midnight approached. Phones rang with calls from local governments, while analysts pored over seismic data streaming in from hundreds of sensors. At 12:23 a.m., the agency issued a bulletin that would reverberate across the entire country, a special advisory warning of the possibility of a magnitude 8.0 or greater earthquake along the Japan Trench or Kuril Trench in the coming week. This was not a routine aftershock notice. It was the first time since the system's creation in 2022 that such an alert had been triggered for northern Japan. The advisory covered 182 municipalities, stretching from Hokkaido down through Aomori and Iwate, all the way to Chiba. Inside the briefing room, a Japan Meteorological Agency spokesperson faced the cameras, his voice measured but grave. He explained that the probability of a megaquake had risen, still low, about 1% for the next 7 days, but high enough to demand special vigilance. This was not a prediction, he stressed, but a calculated warning based on statistical models refined after the 2011 disaster. The message was clear: keep emergency kits close, sleep in day clothes, and be ready to move at a moment's notice.